Wave optics. Introduction. In 1678, the Dutch physicist Christian Huygens put forward the wave theory of light. The wave model could satisfactorily explain the phenomenon of reflection and refraction. However, it predicted that on refraction, if the wave bends towards the normal, then the speed of light would be less in the second medium. This is in contradiction to the prediction made by using the corpuscular model of light. It was shown that the speed of light in water is less than the speed in air, confirming the prediction of the wave model. Huygens principle. Let us consider a diverging wave and let f1, f2 represent a portion of the spherical wavefront at t equals 0 as shown. Now, according to Huygens principle, each point of the wavefront is the source of a secondary disturbance, and the wavelets emanating from these points spread out in all directions with the speed of the wave. Thus, if we wish to determine the shape of the wavefront at t equals tau, we draw spheres of radius v tau from each point on the spherical wavefront, where v represents the speed of the waves in the medium. If we now draw a common tangent to all these spheres, we obtain the new position of the wavefront at t equals tau. The new wavefront, shown as G1, G2 in figure, is again spherical with point O as the center. We also have a back wave which is shown as D1, D2 in the figure. We can use Huygens principle to determine the shape of the wavefront for a plane wave propagating through a medium as shown. The figure shows the geometrical construction for a plane wave propagating to the right. F1, F2 is the plane wavefront at t equals 0, and G1, G2 is the wavefront at a later time. The lines A1, A2, B1, B2, etc. are normal to both F1, F2 and G1, G2 and represent rays. Refraction of a plane wave. Let P dash represent the surface separating medium 1 and medium 2 as shown in the figure. Let V1 and V2 represent the speed of light in medium 1 and medium 2 respectively. We assume a plane wavefront AB propagating in the direction A-A incident on the interface at an angle I as shown in the figure. Let tau be the time by the wavefront to travel the distance BC. Thus, BC equals V1 tau. In order to determine the shape of the refracted wavefront, we draw a sphere of radius V2 tau from the point A in the second. Let CE represent a tangent plane from the point C on the sphere. Then AE equals V2 tau and CE would represent the refracted wavefront. If we now consider the triangles ABC and AEC, we readily obtain equations as shown above. From equation 3, we get the important result that if R is lesser than I, the speed of the light in the second medium will be less than the speed of the light in the first medium. In terms of refractive indices, equation 3 can be rewritten as N1 sin I equals N2 sin R. This is the Snell's law of refraction. Refraction at a rarer medium. Let us now consider refraction of a plane wave at a rarer medium. We can construct a refracted wavefront as shown in the figure. The angle of refraction will now be greater than the angle of incidence. We define an angle IC by the equation sin IC equals N2 by N1. The angle IC is known as critical angle, and for all the angles of incidence greater than the critical angle, we will not have any refracted wave and the wave will undergo total internal reflection. Reflection of a plane wave by a plane surface. Let us consider a plane wave AB incident at an angle I on a reflecting surface Mn. If V represents the speed of the wave and if tau represents the time taken by the wavefront to advance from the point B to C, then the distance BC equals V tau. If we now consider the triangles EAC and BAC, we notice that they are congruent and hence the angles I and R would be equal. This is the law of reflection. In figure A, we consider a plane wave passing through a thin prism. Clearly, since the speed of light waves is less in glass, the lower portion of the incoming wavefront will get delayed, resulting in a tilt in the emerging wavefront as shown in the figure. In figure B, we consider a plane wave incident on a thin convex lens. The central part of the incident plane wave traverses the thickest portion of the lens and is delayed the most. The emerging wavefront has a depression at the center, and therefore the wavefront becomes spherical and converges at the point F, which is known as the focus. In figure C, a plane wave is incident on the concave mirror, and on reflection, we have a spherical wave converging to the focal point F. Coherent and incoherent addition of waves. Consider two needles S1 and S2 moving periodically up and down in an identical fashion in a trough of water, as shown in the figure. They produce two water waves, and at a particular point, the phase difference between the displacements produced by each of the waves does not change with time. When this happens, the two sources are said to be coherent. The figure shows the position of crests, that is solid circles, and troughs, the dashed circles, at a given instant of time. Consider a point P for which S1P equals S2P. Since the distances S1P and S2P are equal, waves from S1 and S2 will take the same time to travel to the point P, and the waves that emanate from S1 and S2 in phase will also arrive at the point P in phase. Thus, if the displacement produced by the sources S1 at the point P is given by the equations shown above, I0 represents the intensity produced by each one of the individual sources. I0 is proportional to alpha square. In fact, at any point on the perpendicular bisector of S1, S2, the intensity will be 4I0. The two sources are said to interfere constructively. Interference of light waves. Young's experiment. If we use two sodium lamps illuminating two pinholes, we will not observe any interference fringes. This is because of the fact that the light wave emitted from an ordinary source undergoes abrupt phase changes in times in the order of 10 to the power minus 10 seconds. Thus, the light waves coming out of two independent sources will not have any fixed phase relationship and would be incoherent. The British physicist Thomas Young used a technique to lock the phases of the waves emanating from slit S1 and S2. He made two pinholes, S1 and S2, very close to each other. On an opaque screen is shown. These were illuminated by other pinholes that were in turn lit by a bright source. Light waves spread out from S and fall both on S1 and S2. S1 and S2 then behave like two coherent sources because light waves coming out from S1 and S2 are derived from the same original source, and any abrupt phase change in S will manifest in exactly similar phase changes in the light coming out from S1 and S2. Thus, spherical waves emanating from S1 and S2 will produce interference fringes on the screen GG' as shown above. The positions of maximum and minimum intensities can be calculated as shown. Thus, dark and bright bands appear on the screen as shown. Such bands are called fringes. Equations 4 and 5 show the dark and bright fringes are equally spaced, and the distance between the two consecutive bright and dark fringes is given by beta equals gamma capital D by small d, which is the expression for fringe width. Wave nature of light. Thomas Young let a ray of sunlight into a dark room, placed a dark screen in front of it, pierced it with two small pinholes, and beyond this, at some distance, a white screen. He then saw two darkish lines at both sides of the bright line, which encouraged him to repeat the experiment, this time with spirit flame as light source, with a little salt in it to produce a bright yellow light. This time he saw a number of dark lines regularly spaced. The first clear proof that light added to light can produce darkness. This phenomenon is called interference. Diffraction. Diffraction is a general characteristic exhibited by all types of waves, be it sound waves, light waves, water waves, or matter waves. Since the wavelength of light is much smaller than the dimensions of most obstacles, we do not encourage diffraction effects of light in everyday observations. However, the finite resolution of our eye or of our optical instruments such as telescopes or microscopes is limited due to the phenomenon of diffraction. Resolving power of optical instruments. Consider a parallel beam of light falling on a convex lens. Because of diffraction, the beam, instead of getting focused to a point, gets focused to a spot or finite area. In this case, the effects due to diffraction can be taken into account by considering a plane wave incident on a circular aperture following by a convex lens as shown. The analysis of the corresponding diffraction pattern is quite involved. However, in principle, it is similar to the analysis carried out to obtain the single slit diffraction pattern. Taking into account the effects due to diffraction, the pattern on the focal plane would consist of a central bright region surrounded by a concentric and bright rings. A provides a detailed analysis showing the radius of the central bright region is approximately given by the above equation. We can apply a similar argument to the objective lens of a microscope. In this case, the object is slightly paced beyond f, so that a real image is formed at a distance v as shown. The magnification ratio of image size to object size is given by m equals v by f. It can be seen from the figure that d by f equals 2 tan beta, where 2 beta is the angle subtended by the diameter of the objective lens at the focus of the microscope. Polarization. Polarization of light establishes the fact that light waves are transverse in nature. In general, polarity represents a state of having opposite tendencies, for instance, positive and negative poles. Polarizing therefore means to restrict any one of the opposing tendencies. Let us consider mechanical waves produced in a string. Suppose we set a rope or string to vibrate in a vertical plane as shown. The oscillations are confined to the vertical plane only. The wave is said to be vertically polarized. If we place a board with vertical slit in the path of the wave passes through it. When the slit is rotated through 90 degrees with respect to its first position, the wave would be stopped. We can set the rope to vibrate in horizontal plane now, as shown in the figure. The oscillations are in horizontal plane only, that is, the wave is horizontally polarized. The slit must be arranged horizontally so that the wave can pass through it. If the slit is in vertical position, the wave would have stopped. Suppose we can use two vertical slits and wish that a vertical polarized wave should pass through the two slits. Both must be parallel to each other. Production of a plane polarized light by reflection. In 1808, E. Lewis Malus found that when a beam of ordinary light is reflected from a surface of a transparent medium like glass or water, the reflected light is partially or completely polarized. An unpolarized light AB is incident on a glass surface. The components of electric vector are indicated by dots and double-headed arrows as shown. The dots represent the polarized light wave whose electric vector is vibrating perpendicular to the plane of incidence. The double-headed arrow represents the polarized light wave with its electric vector vibrating parallel to the plane of incidence. PC is the reflected ray. It consists of a light wave whose plane of vibration is perpendicular to the plane of incidence. Thus, the reflected light, although weak, is plane polarized. This can be verified with the tourmaline crystal. The angle of polarization P depends on the material of the reflecting surface. For ordinary, with plane of vibration parallel to the plane of incidence, and some waves with plane of vibration perpendicular to the plane of incidence, the intensity of this ray is high, but it is partially polarized. Polarization by refraction. When we use a pile of glass plates, the transmitted light can be filtered in such a way that entire dot components are eliminated by successive reflections and only arrow components are transmitted as the light is refracted through them. A number of glass plates are arranged parallel to each other, one over the top of the other in a suitable tube. These glass plates are in contact with each other and are inclined at an angle of 32.5 degrees with the axis of the tube. The unpolarized monochromatic light is allowed to fall on the surface of the first plate at a polarizing angle. Some of the light rays having vibrations of electric vector perpendicular to the plane of incidence are reflected, and the rest are transmitted to the second plate by refraction. The second plate again reflects some more dot components and allows the rest. The process continues through the successive plates, and the outcoming beam will be free of dot components and contains only arrow components. This can be tested by a tourmaline crystal. Thus, plain polarized light can be produced by refraction. Polarization by double refraction. Light passing through a calcite crystal is split into two rays. This process is called double refraction. The two rays of light are each plane polarized by the calcite such that the planes of polarization are mutually perpendicular. For normal incidence, the two planes of polarization are also perpendicular to the plane of incidence. For normal incidence, Snell's law predicts that the angle of refraction will be 0 degrees. In the case of double diffraction of a normally incident ray of light, at least one of the two rays must violate Snell's law as we know it. For calcite, one of the two rays does indeed obey Snell's law. This ray is called the ordinary ray. The other ray is an extraordinary ray or E-ray. For ordinary rays, the vibration direction indicated by the electric vectors in our illustrations is perpendicular to the ray path. For extraordinary rays, the vibration direction is not perpendicular to the ray path. The direction perpendicular to the vibration direction is called the wave normal. Although Snell's law is not satisfied by the ray path for extraordinary rays, it is satisfied by the wave normal of extraordinary rays. In other words, the wave normal direction for the refracted ray is related to the wave normal direction for the incident ray by Snell's law. Ordinary light is not polarized. Looking along a ray of light, the electric vectors make all angles with the vertical. Light that is plane polarized in the vertical place has only vertical electric vector. The plane of polarization is the plane that includes both the vibration direction and the ray path. Light may be polarized by crystals, by polarizing filters, and by reflection. Reflected light is partially polarized following the vibration direction perpendicular to the plane of the ray path. Polarizing filters exclude all light not vibrating in the preferred direction of the filter. Polarizing sunglasses, by orienting their polarizing material vertically, selectively exclude the polarized portion of light reflected by horizontal surfaces. Transparent anisotropic crystals resolve the electric vectors of incident light into two perpendicular electric vectors by the process of double refraction. Upon emergence from the crystals, the two rays add together again according to the rules of vector addition. However, because the two rays have not travelled through the crystal with the same velocity, the combined emerging ray will not be identical to the incident ray. Note that if the incident ray is already polarized, special orientations exist for which all of the incident light is resolved along one of two of preferred vibration directions in the crystal. In this special case, there is no double refraction and the emerging ray will be identical to the incident ray. If a crystal is oriented so that one of its two vibration directions is parallel to the polarizer, then all light emerging from the crystal will be polarized east to west and would be blocked by the analyzer. When this happens, the crystal appears dark and is said to be at extinction. Polarization by scattering. As figure A shows, the incident sunlight is unpolarized. The dots stand for polarization perpendicular to the plane of the figure. The double arrows show polarization in the plane of the figure. Under the influence of the electric field of the incident wave, the electrons in the molecule acquire components of motion in both these directions. We have an observer looking at 90 degrees to the direction of the sun. Clearly, charges accelerating parallel to the double arrows do not radiate energy towards this observer since their acceleration has no transverse component. The radiation scattered by perpendicular to the plane of the figure. This explains the polarization of scattered light from the sky. Polaroids. A Polaroid is a thin transparent film containing tiny synthetic dichroic crystals with their optic axis which are lined in parallel. A modern Polaroid is a molecular polarizer containing long chains of molecules of polyvinyl alcohol oriented in a preferred direction and stained with an ink containing iodine. Polaroid sheets are used as polarizers and analyzers. When a polarizing sheet P1 is placed in the path of unpolarized light, it transmits polarized light with the plane of polarization parallel to the chain of molecules and absorbs the other component. If another Polaroid sheet, P2, that is the analyzer, is placed parallel to P1 as shown in the figure, maximum intensity of light is observed. If P2 is rotated through 90 degrees with respect to P1, as shown in the figure, the light is extinguished. The uses of Polaroids are shown in the table.